Well, I'm back, and here's another fun problem. Figure out the moment of inertia of the system using information provided. We have a pivot point here, two thin rods attached, and here are all the defined variables. You can see that there's some relevant information, but not really useful here. Well, we're going to start solving then. So if we look at the vertical rod, using the information provided, we can just assume that the moment of inertia of this rod is 1/3 ml squared. Well, now consider this. The distance between rod 2's center of mass to the pivot point is the diagonal of a triangle of sides A and B plus L, where A is the horizontal distance between the projection of rod 1 and rod 2's center of mass, and B is the vertical distance between rod 2's center of mass and the point where rod 1 and 2 are joined. So in equation form, d squared, where d is the diagonal, is a squared plus b plus l whole thing squared. Now consider this. The horizontal distance between the projection of rod 1 and rod 2's center of mass and the vertical distance between rod 2's center of mass and the point where rod 1 and 2 are joined also forms a right angle triangle. You can visualize this by drawing a projection out from rod 1 and connecting it to the center of mass. It's also another right angle triangle. And the diagonal of this distance is thus L/2, because it's the center of mass to the edge. Again, if you visualize it, just draw it. So we can expand our previous equation to get this new form, L/2 whole thing squared plus L squared plus 2BL. If you notice, we still have a B in the equation, which isn't a given variable. So to have B in terms of L, X, and M somehow. Well, we can let C be 180 minus X. So just draw the projection out. It's a straight line, and X is the angle between the two rods. So 180 minus X is the acute angle. Since B is the vertical distance, we can get the equation of cosine C equals to B over L/2, which is adjacent over hypotenuse. So with this equation, we can substitute B back and get this new equation. So from here, we are basically done. The moment of inertia of rod 2 is 1/12 ml squared plus md squared, where d is this entire equation that we solved previously. This is gotten from parallel axis theorem. If you want to know more, read up on it. So from here, we solve for the entire system by adding the moment of inertia of both rods. Simplifying it, we get ml squared times 5/3 plus cosine 180 minus x. And as you can see, the minimum moment of inertia is when cosine 180 minus x is 0. That's literally the only way to solve it, where m and l are constant. Which, if you think about it, that means x is 90 degrees, meaning the angle between two rods is 90 degrees. It forms an L shape, and the moment of inertia of the entire system is thus only 5/3 ml squared. Well, that's the end of this question. I'll be back soon enough, or maybe next year.